So good. The recording is started. So good afternoon, morning, evening, good night to everyone to our Geomorphometry coffee talk. These coffee talks are intended to share information about geomorphometry, the quantitative land surface analysis. And for that one, we have scheduled it usually on a bi-monthly basis here, and we haven't done it over the last year or so. But now we restarted it now with Ernest Fahrland on that one. And how it will go that I will quickly introduce to everyone here what is geomorphometry about, making a little bit of commercials. Then I will introduce Ernest, our speaker from today. You already can see him on the screen. And then we will have a 20-minute presentation by him, followed by an open discussion with you all. You are invited. You please speak out. What do you think about it? What he has presented to us, and then we quickly wrap up. So we will be finished in an hour from now. So with that due respect, let me share my screen for 5 minutes. So I just want to make a couple of commercials here. Share, please. This one, share. So the URL for geomorphometry from the URL for our associations, geomorphometry.org. We are a non-commercial, non-governmental association of researchers and experts which want to do something with DEMs. I put it freely here for the exchange, and we want to try to foster the exchange of knowledge and opinions about various aspects of DM, whatever you can do out of a DM. It came out of some of our work. Maybe some of you are aware. Here we have worked on a geomorphometry book together, some of you which are in the call, and we want to advance techniques, knowledge, and even digital elevation models, for digital elevation models. Having said that, you can follow us in various ways. So we will have a biannual geomorphometry conference, which will happen in next year in Perugia, coming that one. And we have also sessions at EGU and AGU, which are organized by different colleagues. Besides that one, the usual Twitter, Instagram, YouTube, LinkedIn data. And with that one, Ernest, I hand over to you and let you have the floor, and please like us, and we're all looking forward to your presentation. Please, Ernest.
Thanks, Hannes, for the introduction. Share my screen, which is currently not possible. Maybe, Hannes, you stop your sharing your ones first. There we go. And I hope it works out that you do see Microsoft PowerPoint right now. I hope that you can understand me. Maybe, Hannes, one small demute to give me just one positive feedback if my voice is clearly to understand.
We can hear you loud and clearly. We can see your presentation, not anymore. Whatever happened? We heard you loud and clearly, but you see the wrong
sharing
button.
The full.
Yes,
I share the full screen. Share it.
Yes, and now
I
click on Ausblenden and not on Freigabe beenden. Ausblenden.
I got it. My fault. Obviously, I'm not as digital as I meant to be.
Okay, go ahead.
Thank you very much. I'll give you an overview of global production processes, and global means really, let's say, almost every pixel on the globe that we have. And so we are talking about roughly 150 million square kilometers of Earth's landmass. And I would like to, let's say, do it as technical as possible. Yeah, you know that in the bottom right, there is an Airbus logo listed. But I try to do it as technical as possible, and also give you a little bit of an insight where the geomorphometry part of our production process comes into play. I have split this presentation into 4 parts, and after a general introduction into DEMs, I would like to show you the insights of the current global radar DEMs, which is basically SRTM as well as the World DEM / Copernicus DEM. And this is also especially listed in section number 3, what the Copernicus DEM, which you are probably all aware about, is about. And then the most, let's say, of the next generation global radar DSM as well as DTM datasets, how we do it. Let's start with a comparison of the global digital surface model. And you can see at the top of this screen, so in February 2000, it started with SRTM, a C-band interferometric mission. I'm not focusing on the X-band section of this mission, so C-band for me is the priority here. But you can see already in the coverage map that because of the orbit inclination, the coverage is not truly global. Yeah? So the coverage is between 60 north and 56 south. And the quality at that time, so we talk about 24 years ago, more than 24 years ago, is, let's say, was quite astonishing. That is, it has to be fair to be said that SRTM was really a game changer in a three-dimensional manner and led to a global coverage of digital height information with a 30-meter posting. The quality, you can see it in the bottom, is moderately good. We all have, let's say, pros and cons on this data set in mind, so I would not emphasize this data set here at that moment, especially because it's not radar-based. A little bit later, also in a Japanese mission, a stereo sensor, a prism sensor, how it's called, was mounted on the ALOS satellite, and that led to an additional Japanese-based surface model. Starting with a 5-meter posting on a global scale, whereas the resampled version of 30-meter posting is now free and open available and is heavily used in the geoscience community. And you can see already in terms of the root mean square error that this was a big step forward in terms of level of detail as well as vertical absolute accuracy. Then the German government in a public-private partnership has launched the Tandem-X mission, the 2 satellites TerraSAR-X and Tandem-X as displayed here on the top. And that is an X-band interferometry mission which acquired data between December 2010 and January 2015. The huge amount of raw DM data has then been combined into a global coverage with 12-meter posting, 12-meter ground sampling distance, but it's fair to say that every of the already mentioned data set can be resampled to lower resolution as well. So that's why here I display a 30 as well as a 90-meter dot as well. What is a next step in terms of relative accuracy and absolute vertical accuracy is here displayed in the bottom. So the LE90 has been calculated many, many times by researchers as well as Airbus as the provider of this data set. And with 2.5 meter, the absolute vertical accuracy is another step forward beyond the ALOS version. And then already in, let's say, heads up for one of the later slides is the World DEM NEO data set. And now the vertical accuracy has again been, let's say, improved. And we do talk about a new temporal footprint. So 2017 to 2020 and a little bit ongoing, but I will come to that later. And we do talk about a 5-meter post. That should give you, let's say, an overview. There's obviously a voice in between, so I kindly ask for muting. Let's talk about the production of current global radar DEMs. And now it's emphasized here and highlighted. So the ALOS dataset in between is now suppressed. The SRTM dataset as the game changer more than 20 years ago. It has been processed by the Jet Propulsion Laboratory. After the landing of the Endeavour shuttle in the year 2000, and then a ground segment of in the ground segment and topographic processing subsystem has been enabled, as well as a mosaic processing subsystem has been enabled, and of course a quality assurance subsystem is linked to both production sites, sub-processes. Let me phrase it like this. With the more recent TandemX mission, which led to World DEM, it's more or less the same. Yeah, so there is an interferometric part which transfers the phase information of the radar signal into raw height information. And then this raw height information is calibrated and mosaicked to each other to create a homogeneous global coverage of digital elevation information. So this is the top level overview to create unedited, respectively unfinished digital elevation information based on radar. So what DLR, the German Space Agency, has applied for the TandemX mission is very comparable to the SRTM mission. It is fair to say that this quality assurance box here in the left is of course applied by DLR as well, but it's not part of this figure here. So there was a dedicated quality assurance work step at DLR as well. So, long story short, there is a similar process designed for producing unfinished radar-based DEM data. But what do you do with these unfinished data sets? There are radar-specific structures or artifacts in that data set, mostly related to very steep terrain, which inherits layover structures or radar shadow structures or gaps, and especially the hydro features, because of the smooth surface, require an editing step. What has been done in SRTM is 2 independent teams from the industry were contacted to apply the finishing of the SRTM mission, whereas for the TandemX mission, it was one sole team led by Airbus to run this production finishing. In the past, 2 independent software packages have been applied. One was SocketSet by BAE Systems, and one was the soft plotter software from the Boeing company, whereas now for the TandemX mission, a dedicated, tailored DEMs software has been developed and applied to run the global production. The peak personnel for both finishing processes was up to 80 to 90 people working in 2 shifts, so in the morning shift as well as in an evening shift, which already brings you to the point, this is not a fully automated processing. In this time of the early millennium, right after the year 2000, respectively right after the year 2015, manual work was a heavy package of finishing radar-based DEM datasets. The target for the SRTM mission was roughly 20 hours per 1x1 degree cell. I don't know if this is, let's say, the actual measurement already, but I feel confident that 20 hours per geocell are a very good target estimation. For the TandemX mission, 17 hours of manual workload were required to edit every 1x1 degree geocell. The question is now, how do you compare these 2 productions? Of course, in the SRTM times, roughly 13 million pixels cover one cell of SRTM data because of the 30-meter pixel spacing. With World DEM, this has heavily increased, so roughly 81 million pixels have now to be edited per geocell. And by the way, we talk about roughly 20,000 geocells or working units in the TandemX frame. On the lake criteria, this has now been reduced. It was required to reduce it because the level of detail of the input data required so. We talk about roughly 86,000 square meters in the SRTM times. There was a dedicated length and width criteria for lakes. Now this has been changed to an actual measurement of the aerial coverage of every lake. If this is exceeded, the lake will be edited. If not, it's not edited. And the same is also transferable to a river width criteria. What do you planarize in terms of? If you compare it now, then I would say that the tandem X production is roughly 7 times more performant than the SRTM times, which show that the technological evolution of software packages and scripting has really put in a huge, let's say, impact on the world DEM production, the tandem X-based one here. And this is especially astonishing when we talk about roughly factor 12 in terms of more detailed editing criteria. So long story short, both data sets, SRTM as well as World DEM and Copernicus DEM, required many, many years of manual workload. We talk about roughly 5 years in the SRTM days. So the finished data set of SRTM has been published in 2005, 5 years after data acquisition. And for World DEM, we talk about roughly 3 years of the global finishing of the tandem X-based data set. So users had to wait 3 years, respectively 5 years, to get the DEM data. A little bit of an, let's say, insight into the software packages. To be fair, the snapshots on the left-hand side are just gray because the scientific paper is in gray colorization. Of course, the software is much more colorful than displayed here on the left. On the right-hand side, the software that Airbus has developed here is also displayed. And you can see on the bottom right, the dual monitor setup for editing the height values with the possibilities to tilt and rotate terrain and to put seed points, for example, here into these this reservoir that you see here in the top and in the bottom of that snapshot. So whatever was feasible in terms of automation has been considered for the DEMS software to make this global challenge of 150 million square kilometers editing as performant and as economic as possible. This World DEM dataset now is the main driver, the primary input for the Copernicus DEM that you likely are aware about. So the World DEM is the primary source for the Copernicus DEM. It's a public-private partnership of the German Space Agency, DLR, as well as Airbus Defence and Space. And both satellites, TerraSAR and tandem-X, were flying and are still flying in a bistatic information. The primary mission goal of the tandem-X mission was the generation of a global tandem-X DEM, and this has been fulfilled. A consistent terrain and hydro editing to create the World DEM is also fulfilled and finished. And finally, the corrective and perfective maintenance in the frame of the Copernicus DEM is already finished. And Copernicus DEM is now available at a 30-meter pixel spacing, free and open for everyone around the globe. And just to give you an insight here on the coverage, on the bottom right, there's a free and open access to the 30 and 90-meter data set of Copernicus, which is World DEM based. And there is a restricted Copernicus user access for the European continent, as well as the French overseas departments. That was the manual part of editing radar-based elevation data. Let's focus on the production of the next generation of global radar-based surface models, as well as terrain models. After the launch of the commercial World DEM product in 2018, this blue star should highlight this point in time. There is a yellow period where Airbus has received lots of user feedback about this World DEM dataset. And right after that, in the year 2021 and 2022, a user survey has been conducted and the results are that the multi-date weighted combination of all these tandem X scenes to one coverage are not really preferable. So it's not possible to trade a date, How do we do it? How do we do this fully automated production? And let's focus on the surface model first. The historic World DEM data in its 12-meter posting is downgraded to a 30-meter resolution data set and has been transferred to the German Space Agency. And the colleagues from DLR are using this data set to support one key part of the interferometric process, which is the phase unwrapping. And so the edited global world DM dataset is also available at DLR to support the future phase unwrapping as well as the absolute calibration. But it's important to note that the height values that are created here on the left-hand side by DLR are complete new and independent height values from the old world DM30. This dataset is then transferred on a raw DEM scene basis, roughly 30 by 50 kilometers, to Airbus. And we do have established a database that tracks every raw DEM scene. What do we do with these scenes? First of all, we have to decide in the overlapping areas which height value is preferable. You can see here in the top left part, there is a forested area right next to this white spot, whereas 1 year later or half a year later, this forest is now cut. So what do you do? What does the user want? We can either apply a temporal filter, so exclude the scenes from 2019, 2020, or we can establish a standardized process where in the overlapping regions of the raw DM data, the best pixel is pushed through, but with a focus on the most up-to-date scene, so with a focus on data freshness. And this is what has been established here in the World DEM Neo time frame. This mosaic of unedited, fresh height information needs to be corrected, respectively finished. You have learned a couple of minutes ago that in the past, there was a manual delineation of artifacts, and then these artifacts have been corrected with manual interaction. Nowadays, we have fully automated, but we have not developed everything completely new. Please focus just on this formula where the cursor is circulating right here. What is important is there is an HEM abbreviation in it. The HEM is a height error data set that comes with every pixel from DLR. And what DLR has established for the Tandem X mission is a weighting of all the scenes with a focus on quality. So there is a quality information available for every pixel around the globe. And what we have done at Airbus is we have taken this formula and have improved it or adapted it in such a way that there's now a certain stretch factor considered, which sort of plays with the height error from the historic data set. It's either improved or it's either decreased. Both let's say, possibilities are applied here. And this allows us on a pixel basis to really pick the best pixel of the fresh scenes. And if the height quality of the fresh scene is simply not sufficient, then this height information is replaced with the historic World DM dataset. And this is what we do fully automated within a couple of minutes. How does this really look like? And I hope it works out now with the internet bandwidth. You can see in the center of this screen a raw DEM as it looks like by DLR. What is important also is this height error map here in the bottom right. And you can see some red colorization. I'm just using a traffic light system here, so red means bad data. And you can see that many of these slopes that you see here in this north up display are colored red. These are the layover artifacts that we have in our raw DEM dataset. And this is definitely not acceptable in terms of DEM applications and analysis of this dataset. Those are the structures that need to be replaced as accurate as possible. We do have on the top right the edited but historic world DEM surface model. And with the formula presented a couple of minutes ago, we are now combining the historic world DEM dataset with the new elevation information from DLR. And finally, we achieve on a pixel basis what we can see in the top of this screen at the top center. And I think it's obvious that there are no artificial barriers or boundaries or shears visible in this data set. So the fully automated combination of the edited but historic world DEM dataset and the unedited but fresh scene from the German Space Agency works pretty well. There's just one tiny part left that needs to be applied, and this is the focus on the hydrological editing. Just another 5 minutes, and then I will be done for the Q&A session. So what we do is we do fully automatically classify the water features that we see in the unedited acquisitions, but it has to be emphasized that we cannot use any historic water information because of the temporal gap between the two data sets. We need to find the water extent and water level as visible on the date of acquisition by the German Space Agency. So what you can see here is the historic reservoir as we have edited in the world DEM dataset. It's huge and big, but you can see already here that there is some structure on top now of on this reservoir. As a side information, this is in China, and a huge solar farm has been applied here or assembled here on this reservoir, so a floating solar farm. And you can see here that the height error is quite acceptable for the majority of the solar panels, but this narrow strip in between needs to be edited. So we have to find the water areas which we don't trust in the fresh acquisition. And this is what we do fully automatically for ocean, lake, as well as river features. Finally, we of course apply a statistical analysis based on ISAT-2 laser altimetry data. And we are very happy with the results because we have definitely not decreased the quality from the historic world DEM dataset. We have in fact increased the statistical outcome of this analysis by being better than 1.5 meters in the bare ground plain terrain areas. Why do we need fresh height information? Because Earth topography is changing. Open pit mining is changing the Earth topography. There is huge deforestation in the tropical rainforests around the globe, but also in the boreal forests in the north. But this example here is from Brazil. And you can see that now the Earth's surface, the true top reflective surface, is changing. There is infrastructure work. We don't see it here in the historic world DEM dataset, but after the animation, you will see a road passing through this scene as well as an industrial site here in the bottom right. And last but not least is a huge construction area linked to the One Belt, One Road initiative in China. And the already historic world DEM dataset from 2010 to 2015 is locally significantly changing with the fresh acquisitions that we receive from the German Space Agency. So from our perspective, there is definitely a demand to keep elevation information as up to date as possible. There's one big challenge that we still face. Radar does not work perfect in the urban environment. What we need to do and what we have established is a dedicated process which compensates for urban structures, but we are still using radar. But we do not do interferometry. We are using a machine learning technique which reconstructs urban height information based on the SAR amplitude. And if available, for example, observing and building from the ascending as well as descending orbit, then it's possible to reconstruct the elevation of the buildings. And we will now see here alongside this dashed line in the top. And you can see on the right-hand side, this is the 5-meter WorldDEM NEO. And I would not say that these are actual building measurements because of the interferometric processing. But now with the SAR to height image reconstruction, I think it's fairly good what we can achieve in terms of building structures in the urban landscape. And it's a goal from Airbus to do this on a global scale and further improve the global elevation models that we have by integrating this technique into the global database. And finally, because there is this demand for a global DTM, we have gained experiences with the historic WorldDEM data set to go for a global bare ground information. We have launched this product in 2018, and at that time it represented the very first true global and full consistent digital terrain model, which was only available on a commercial basis. But we have gained experiences in fully automated processing. And today we benefit from this experience and combine this into the new 5-meter digital surface model and create a new bare ground coverage of WorldDEM NEO DTM. How do we do that? And that is the very last slide. You can see the level of detail that we have in our WorldDEM NEO DSM, including single tree rows and hedges, and also some urban agglomerations here in the bottom left, and of course the clear structures of the forest areas that we see. We have developed a quite sophisticated classification algorithm to identify urban areas as well as vegetation areas. We have established a removal process to subtract the height information that we see in the surface model to come to a fully automated, best as possible bare ground information, including a local filter to clean up the data. It's fair to say that we are using ISAT2, which somehow penetrates vegetation as a support of the shift of large-scale forest areas. And after filtering, this is what we achieve on the right-hand side. It's definitely not comparable to airborne LiDAR data, but I think on a global scale, with the consistency that you all know from the Copernicus DEM and the Tandem-X mission, it is a quite acceptable bare ground model that we can now create. Having said that, I would like to say thank you. This is, let's say, flashback to the last geomorphometry conference in Iași in Romania, and which of course is available as a DTM. I really appreciate having the chance to present this topic here in the frame of the ISG Coffee Talks, and I'm happy to answer your questions. Thanks.
Thank you, Ernest. Really interesting talk
I learned so many new things today. You know, with SRTM, and then I was thinking, ah, that's interesting. Okay, yes, was my first, one of my first processing, and ask questions. Anyone who wants to break the ice, raise your finger or just come up and then turn on your video so we see you.
Just one very small FYI to you, Hannes. The very first statements from you were very hard to understand, at least for me. I don't know if this was local bandwidth trouble or global one, but what I gained is
local
that you
local bandwidth. My internet connection has broken down, and you have me now on the phone. So this is German mobile phone technology working for you at its best. Such a interesting service. Okay, so then let's everybody see if someone has wants to have the floor.
Okay.
This is Giuseppe. I will break the ice of the question. Ernest, I have a question for you. So for the digital terrain model, you guys have implemented a correction with ISAT. Can you say a few words about this kind of correction implementing the ISAT? And in case if you're planning also to integrate with the JEDI data due to they have a very wide coverage.
Understood. Happy to answer that. So what we do is wherever we are using the ATL-08 product from the ISAT-2 mission, which provides canopy information as well few terrain information in the dense, let's say, forested regions. Wherever we have these terrain points of sufficient quality, so there is a quality filter applied. We are using that background information to compare it with our top canopy that we have in the DSM. And this finally supports the, let's say, shift height that we need. Because we are also measuring the object height surrounding every feature. And if you have surrounding height information as well as few anchor points in between, the shift surface becomes more or less more robust. And then we apply the shifting. This is what we do. We do not intend to consider JEDI footprints because of the inconsistency at the 50-55 degree border when JEDI is not available anymore. So we are focusing on ISAT and have tested with JEDI, and it became obvious that as a single source, ISAT is beneficial because of consistency reasons.
Okay, clear. Thank you very much.
Got it. I can see Sebastiano has raised his hand.
Hi, hello. Thank you for the presentation. Very, very cool product. I'm wondering if the new DTM now, with respect to the Copernicus DEMs, which kind of improvement you were able to gain in steep mountains, because probably Copernicus DEM has a lot of gaps in steep mountains. So I'm wondering the improvement in this kind of setting.
So let's say the influence of external DEM data that you experience in the Copernicus DEM or World DEM is reduced, but it's definitely not replaced. It remains a side-looking system, and we will still face radar shadow as well as radar layover. There is one big benefit because DLR has changed the looking direction from the historic World DEM to now the, let's say, new acquisition phase. So we can somehow compensate few shadow areas from the past with, let's say, the opposite looking direction. But be aware that, let's say, the steepest slopes of Mount Everest, Matterhorn, whatever we have, will never be comparable to LiDAR. So the influence of external data is reduced, but not replaced.
Okay, someone else,
Thank you.
please hand up or turn on your video so we can see you. I have a question if no one else wants to have the floor, because for the moment I don't see anyone else having the hand up. Ernest, you were mentioning that you are placing sometimes pixels, or maybe I misunderstood, you're placing pixels if they are not matching with some pixels from the old world DEM in your product, or maybe I misunderstood. And then if I really correctly understood, then the question was for me, how do you ensure hydrologically consistency or DEM consistency if you replace that single pixels or this number of pixels?
Got it. So let's focus on the first part of the question for that moment. So very pragmatic. Whatever we have a quality information for the historic data set and the new one. If the new height information is reliable, take it. So that is the task for the computer. Take it, push it through. If this is not sufficient, replace it with the historic world DEM data set, because it's the best alternative. It's the best alternative, free from void, hydrologically edited. Or let's say flattened. It's not hydrologically conditioned. That is, let's say, a slightly different thing. On the DSM part, let's say the hydrological conditioning in the mountains is, let's say, not really ensured. There are forested areas that we have in between. There are some lakes which are wider or narrower at some, let's say, locations around the globe. And when a river is, let's say, too narrow to be, let's say, captured by the radar sensor, then there is an interruption in the DSM. But on the DTM part, it's slightly different. We have, let's say, made a good progress in terms of when we detect a river and start to planarize it, we ensure sort of a flow to the ocean. But this is one of the most sophisticated tasks that you can imagine. Yeah? So for me, fully automated DTM editing is the holy grail if you achieve that. And so far we have, let's say, many ideas, and we have it in the R&D development team here at Airbus, but it's not fully implemented in this current version of the DTM level 1. It will be in one of the next evolution steps. But this is one fair point here. Because the production time has now significantly reduced, we can easily play around with parameters or specific functions in the production process, and then apply a reproduction of the globe. And then few weeks later, a new global coverage with new sufficient quality, it would be available. So that is, let's say, the very first part is maybe sufficient for you in terms of quality. The hydrological part is another technical challenge that we are currently working on.
Thank you, Ernest. There is Ian, please come in.
Audio, video. Hi. Oh.
Hi, Ian.
Just a moment.
Now we see.
The time lag. Oh, there we are. Okay. Can I ask about how you treat marshy ground? You mentioned you've dealt with all lakes and corrected them down to 7,000 square meters. I think in the early Tandem X there was a problem also with marshy ground. The even the partial reflection from the water areas within the marsh could cause problems.
Correct. That is correct. So we did not focus on specific ecosystems or land cover in the production. So we do not put a certain emphasis on vegetation or marsh or saline areas or urban environments. It's purely focusing on the quality that the raw data looks like from German Space Agency. If this is sufficient, if this is good, push the height information through. If not, compensate it with the historic world DEM. If we transfer it now into radar geometry, marsh is, let's say, usually quite, it's not that smooth compared to an hydrological feature. There is a certain texture, like grassland. So in, let's say, my visual memory, having seen lots of places in the global DEM data set, whatever the sensor has measured in marsh areas or plain terrain areas is perfectly displayed in the surface model. So it's an actual height measurement without any signal penetration into the ground. We have not faced it. We face a bit of signal penetration in the heavy, dry, sandy areas at the Arabian Peninsula and a little bit in the Sahara. And of course, the standard penetration into vegetation, but the marsh areas look very good. And even the raw signal from DLR is a very good quality. But if you want to see and assess it by yourself, I'm happy to provide you a sample.
Right. Thank you very much. Yes, that's great.
So just, yeah.
Ernest, that was the next question we had from our colleagues in, I think in Asia, which was asking, you have play around and what would be the expected accuracy for the DSM and DTM from the WorldDEM Neo?
Hannes, that was very hard to understand. Sorry, there was again many audio interruptions.
Hang on.
Apologies.
Okay, sorry.
Why don't I read it out instead of Hannes? Thanks for an interesting presentation. I have two questions about WorldDEM Neo. Which way we could get the WorldDEM Neo that has amazing performance? Are there any data samples that can be accessed and tested? And the vertical accuracy of WorldDEM Neo, DTM, and DSM.
Got it. Now I thank you, Ian, for stepping in. So at this moment, the WorldDEM Neo is a commercial data set. There is sample data available on an Airbus website, and there is the chance to reach out to us and contact us, for example, for sample areas of a specific spot on the globe, and then you can do your own assessments. We are very much interested in any independent feedback, including publications on conferences. So feel free to reach out for your area of interest to us. Maybe it's not 150 million square kilometer sample, but a subset of it. And then we can talk about providing you a DSM and DTM sample for your own quality assurance. That is the political answer on that. Is that correct? Does that answer the question from the colleague? Good. Thanks, Hannes. Thumbs up. So feel free to reach out to ernest.fahrland@airbus.com, and I'm happy to support you.
Good. With that one, I don't see anyone else having the hand up. Do anyone else from the audience see someone else with hands or anything in the chat? Because I don't see anything. And then let's give virtual applause to Ernest for this morning's, evenings, afternoons, nights presentation. Ernest, you moved us today throughout the history of mainly radar-based DMs. You showed us how certain things have been edited in the past, and you walked us up to date for what's the current state of the art or world, the world standard from Airbus is currently. What are you doing currently? Thank you very much. I think, at least for me, my side, it was really interesting, and for everyone else also in the call here, because we learned a lot how certain things were done in the past, which we elevation models, if we try to do something, if we try to deduce something. That one, thank you, Ernest, again. Thank you, everyone, for attending today. And we will see each other in 2 months' time from now. And for the next coffee talks, please look at the Geomorphometry website under the section Coffee Talks. And apologies for my issues today. I'm really sorry for that one, but my internet is still gone, and so I hope you could still hear my audio summary of today. With that one, thank you very much, everyone, and have a nice day.
Thank you very much for having the chance to present this
Bye-bye.
topic, and Merry Christmas.
Thank you very much. Bye-bye.
Okay. Bye-bye.